All right, so we will finalize today our flow around sphere. So basically, what did we do? Okay. So just recall we are doing, oh, hi. Okay. Okay. Huh. Just a moment. Okay. Oh, we have to reopen this. Or all right. Now it should work. So recall we are solving, or we have solved really, for velocity. Oh, it's still not on. Now it should be on. Come on. There we go. I've noticed, and literally in the last 2 weeks or so, that sort of reaction time to every time I'm connecting this VGA to the projector, there's a delay. Now, I don't know what, but I keep experiencing this. All right. So we're solving for velocity distribution around a sphere, very slow flow of Newtonian incompressible fluid, and we have, by analyzing the problem, decided that we need to be in spherical coordinates, and we are really, since we have symmetricity in the phi coordinate, we are really, everything is depending on r and theta, but we can't get rid of either r or theta as dependency. And we also have two velocity components, and we can't get rid of one of them as we normally do to simplify the problem. So because of that, we had to go into the entire new sort of way to solve problems. We couldn't just go take equation of motion or those appendices, like in Appendix B, you actually have Navier-Stokes equation that is kind of ready to go, that you can plug things into, because it wouldn't simplify to something that is solvable. We actually had to go and take the curl of Navier-Stokes equation in order to get rid of the pressure dependence. And then we kind of massaged that into the equation of vorticity being curl of velocity. And that looked much more complicated, except that for 2D flows, we can actually apply streamline approach. Okay? We have introduced streamlines as basically curves, or stream functions are functions that are constant along a curve, and that curve in a steady state flow coincides with the sort of a path of a particle in flow. Okay? So streamlines have basically a relationship with velocity field. If I know the velocity field, I have equations that I can easily integrate first order to get the stream function. Otherwise, we will actually, in this approach, actually solve for stream function and then plug it into those equations and find the velocity field. So that's essentially what we've been doing. Basically, what the vorticity equation comes down to that we introduced the operator nabla 4 of this stream function is equal to psi. Psi is stream function. And this is in any kind of stream function approach which you apply when you have flow, you will use it in sort of spherical coordinates when you cannot get rid of one of those velocities and you have two that depend on two variables. This is where you actually go and apply stream function approach. Okay? So when you have this complex problem, and this is basically what you're solving. And we had boundary conditions. We kind of needed to translate them in terms of, so I'm just like conceptually explaining what we were doing without giving the details, because we went through the details last time. Translate to what do they mean in C, right? And in spherical coordinates. And boundary conditions are very important to look through. Our major approach in solving partial differential equations is separation of variables, and actually boundary conditions kind of complied with that. Okay? So boundary conditions gave an idea that separation of variables, meaning C of r theta is assumed to be some function of r times some function of theta, should work. That's your first test. If you look at the boundary conditions and they're not complying with that, then, well, it's not going to work. And not only that, when we actually looked at the boundary conditions, we were able to put conditions or find what g of theta was. Okay? And basically, when we plug things in, into boundary conditions, we actually got that g of theta is sine square theta. That was crucial in actually simplifying. So once I have this Laplacian, then we actually just went to use this form for spherical coordinates from table 421. And when we plug this presumed function psi into that equation, we were able to find if our assumptions didn't stop there, f wasn't directly findable because I had a fourth order ODE. Okay. But we assumed, so basically we got fourth order ODE on f of r. And we assume general form of a power function, so r to the n and see which n work. Fourth order equation, of course we found 4 of them. Okay. So now our solution can be assumed to be superposition of those. And once we assume that and plugged it into the boundary conditions, we actually get what the coefficients in that superposition are. Does that kind of ring a bell from what we were doing roughly? So this is basically a summary of what we've done so far. And we're basically, so then apply BCs to f of r, which we found was, it was C1 divided over r plus C2r plus C3r squared plus C4r to the 4. So those are all the possibilities that work. And we found C1. So find C1, C2, C3, C4 from boundary conditions. That ultimately gives us solution. Vr of r theta is v infinity, that was that velocity away from the sphere, 1 minus 3/2 radius of the sphere over radial coordinate plus 1/2 r/r to the cube cosine theta. V theta of r theta is minus V infinity minus sine theta. So that was quite a bit of work just to get these velocity distributions. How am I going to get pressure? So vorticity equation doesn't help me, it doesn't have pressure, we kind of killed it. Okay? So I will now go back to Navier-Stokes, or actually Stokes equation, since this is a creeping flow. Stokes equation apply. Okay? The simpler the better. If you can find the simplest equation that applies, do that. Okay? So Stokes equations apply, and then basically you can plug things in. You will still have to go, so basically now we actually, to find pressure, use Stokes equation, or the simplest equation that applies to the problem. One simpler one would be Bernoulli equation, but this is not irrotational flow, so unfortunately not. Not here. But that one actually gives the simplest result. And basically that would give you that to find pressure, use Stokes equation or Navier-Stokes or Bernoulli if they apply. So try to find the simplest. Applicable. So I will let you work out the details. Again, that's going to be part of your homework. I'm just going to write down the intermediate steps. So basically that would give you the dP dr is equal to 3 mu V infinity r square r over r cubed cosine theta. And dP d theta is 3/2 mu V infinity over r over r square sine theta, where P is generalized pressure. I need a boundary condition on pressure to actually solve this, otherwise I'm solving it plus minus constant. So we're going to give ourselves this constant. We're going to say, P is P0 at Z is equals to 0. Far away from the sphere. So that means as r tends to infinity. So that plus minus constant that I actually have when solving this is going to be P0 minus rho gz, essentially, away from the sphere. So this just means if I didn't have the sphere, my pressure is some pressure P0 plus the hydrostatic pressure over P0, okay? Or minus, because we're pointing upwards. So we can also see that basically I also have for pressure that it's a function of r times function of theta, so I can actually use that when I see that. So my function of theta should be cosine theta, because when I look at the partial p partial theta, I have a sine, so that works out, right? If I have a separation of variables, where I'm doing partial derivatives, they kind of work separately on these functions that I put in there. So then it's relatively easy to see that my pressure should be B0 minus rho GZ minus 3/2 mu V infinity over R over R squared cosine theta. Again, don't be afraid to use the separation of variables, and I'll let you work out these details.
So you're just picking an arbitrary z equals 0 to say p knots out?
Yeah, you gotta give yourself, that's what you always do with pressure, right? You have to have a data point where you start your measurement from.
I don't understand how we got the first two ones. Like del P by
That came from plugging things into the Stokes equation.
Okay.
I left out the details, so I'm leaving you those.
Stokes.
Yep.
I thought we were doing numbers.
Navier-Stokes applies as well, but it's in this case you have creeping flow. In creeping flow you can always. So always go with the simplest one you can. So Navier-Stokes applies as well. Right? Okay, so now we have everything. We have velocity, we have pressure. You'll work out how actually plugging things into Stokes equation. So now actually let's finally, I motivated this whole solution, and that was now 2 weeks ago. I motivated it with the fact that in a lot of applications I have particles in the flow. I should know what the force is in those particles. That will tell me how fast it takes for sediment to settle down. That will take me. That will tell me how effective it is when I'm moving on propellant in my hydraulic fracturing applications. All kinds of. We either have naturally occurring particles in the flow, or we actually put them in ourselves. So of course we need to know that. Second thing that we have is technically when I'm flowing through the granular medium, I'm flowing around particles, and I can imagine that they're spheres. Okay? So we will actually find a way to generalize or find permeability through a sphere pack, and you probably tossed around quite a number of formulas in petrophysics. We will actually derive them. Okay? There will be smile. And you can now see why this was not done in petrophysics. They were kind of presented with the formulas, because building up all the tools to actually do it is not necessarily what petrophysics is about. So basically, we will actually have two approaches. One will be this stream function / what I will call unit cell approach to find permeability of a sphere packing. And another will be actually deriving carbon causating with those tortuosity constants and so forth. So it will be fun. So those are going to be our porous media applications. But before that, we need that force. So let me just hint, how will you find force? So basically, I am wondering what is the force exerted by the flowing fluid on the sphere. So we know that we have viscous forces and we have pressure forces. And there's a specific tensor that combines both. This is static sphere flow. So what is the tensor, stress tensor that combines both? We had that big combined one that also had convection in there, but here I have a static sphere. Then we had what? Pi, yeah. So that is going to be the tensor that is going to be helpful. So if I remember, in general, by definition, what was pi ij in terms of forces? Now, in the meaning, what is pi ij or tau ij or whatever? It's a force in which direction? J direction, exerted by the fluid in lesser I, so basically in ith direction, right? So force in J direction, okay, exerted by the fluid in lesser I onto fluid in larger I direction. So now if I have a sphere, okay, I will have to look at all of the forces. Okay. Sphere specifically sits in the region of R that is less than my uppercase R, right? And the fluid is in the region of larger R, right? So for one, I will have to take a negative of the shear stress, and then look at, I will have shear stress, and I will have to apply it to an area, surface area patch on the sphere, okay? And I will look at three components possible, right? So if I'm looking at the normal component, I'm looking at the stress component PRR and its action, right? So if I'm looking, basically I will have force on a patch. Let me draw. So let's say that I have a patch here on a sphere. Okay? And I know that I have delta R, have delta theta, and I have in this direction delta phi. So this is my coordinate system on the sphere. Then normal force per unit area, normal as in normal to the sphere surface, per unit area is minus PRR delta R, okay, times area of that patch, right? And this, of course, evaluated at R is equal to R. So I will basically integrate this over the sphere surface. Okay? And that will give me one contribution to the total force. Okay? Then I will look at also, or you will look at tangential forces. Okay? So I will also look, so I'm wondering what is PR theta and PR phi doing as well. Okay? And integrate them as well. What are these forces going to integrate to? Again, some force in some general direction altogether. Okay? Because of the symmetricity of the sphere, what am I, so I have sphere like this. This is my general z direction in my Cartesian coordinates, right? And I have flow that is coming in, going around the sphere, and then coming away. And it's equal to infinity file. What do I expect all of these forces, because I have these multiple forces that I'm integrating. And remember, delta R changes around the sphere, so in order to integrate, you have to express it in terms of delta X, delta Y, delta Z that don't change around the sphere. So I'm going to sketch that out in a second. But just physically, what do you expect this force, overall force, once you integrate all of the components? Z direction, right? So basically anything that you get in X, Y direction should go away. And if it doesn't, go recheck your calculations. And you will get a force in Z direction, okay? And we will look at the total force that we get there, okay? And it's typically, you will, in formulas, we will arrive at something called Stokes formula for the force. That formula is just a number. That's actually, force is a vector, its direction is in the direction of the flow, but the number is the value that we actually compute and work with. So, just a reminder, so if I wanted to integrate this part of the force, I'm going to call this normal force because I'm integrating component normal to the surface. So my normal force is basically integrated 0 to 2p, 0 to p. So PRR is tau RR plus pressure, right? Times 1. So it's minus pressure plus tau RR, evaluated at R is equal to R, times delta R. And then my area of the patch is, what is the R square sine theta d theta d phi. Yes? So this is surface integral in spherical coordinates. I have some function, and it's actually a vector function of R here. And then this is my little area that I'm integrating in theta and phi directions. Okay? So remind yourself, so this is a surface integral in spherical coordinates. So there is, look at the appendix. I'm forgetting which appendix, but it's appendix A somewhere where so you can find the formulas there. And now, before we can actually integrate this, we gotta break down this delta R to something that is not necessary, or what is its dependence on theta and phi before it can be integrated. And again, if you look back into the you will see that delta R changes around the sphere as follows. It's sine theta cosine phi, delta x plus sine theta sine phi, delta y plus cosine theta delta z. So basically I will have three integrals. And I have to go and find what is P plus tau R, right? P, pressure, we have the formula for pressure. In that formula I have rho gz, I have to remember that z is R cosine theta before integrating. So, second thing, tau RR. I can go and just plug in my velocities into the equation. Or I can remember something that we did in class about the viscous forces normal to the surface in an incompressible Newtonian flow. What is tau RR? It's a stress, viscous stress normal to the surface in incompressible Newtonian flow. It should be. It's a good guess, right? Yeah. So go back. We actually did derive that after equation of continuity. So tau RR, specifically here at the surface, not necessarily away from the surface, is equal to 0 because it's a viscous stress component normal to a solid surface for incompressible Newtonian flow is 0. But again, if you actually plug in, if you plug in your velocity distribution, you should still get the same. Okay? Just a little longer way there. Or plug in VR, R theta, V theta. V theta won't be in here, but VR. It depends only on VR. And work it out. And my pressure at R is equal to R is that P0 minus rho g z, z on the sphere is radius times cosine theta. So basically the way I go in between these two coordinates is like that. Minus 3/2 mu v infinity over R cosine theta. And then you integrate to get that normal force. So x, y components will be 0. And if z of this normal force, when you integrate, you should get 4/3 PR cubed rho g plus 2p mu r v infinity. So this is the delta z or z direction force. Lots of work, and I actually skipped all of the little steps that you will fill in. But we're not done yet. So we integrated now only the normal component. We need to integrate all of them. So basically tangential forces we would now basically, instead of tau RR, we're going to look at tau R theta. You can guess that tau R phi is actually 0 because of the symmetricity and the V phi being 0. So it's basically minus tau R theta evaluated at R is equal to R. I don't have the pressure because this is the shear. And then this is what direction? Delta theta, right? And my surface element is this. So basically this is tangential force on surface patch. and I have to do minus because, again, my fluid is in the region of larger r and the sphere is in the region of lesser r. So now I need to integrate this. So it's the same procedure. Integrate, same as before. You will need to find what tau r theta is from velocity distributions. You will need to express delta theta, right? So this is from velocity distributions. This needs to be expressed in terms of delta x, delta y, delta z. Okay? Again, x and z components of this force will integrate to 0. And the only survivor will be in z direction. So when you actually do that, Fz, I'm going to call it tangential component, dot, 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 after integration will be 4p mu r v theta. And then note, of course, tau r phi is 0, so we're not considering it. So my total force, only z components survive, okay? And when I add them up, I will have this 4/3 PR to the cube RG. What is this? Buoyancy. So this is buoyant force. This is my volume of the sphere, and I replace this is rho of fluid, right? Okay. This is the buoyant force, and then the rest is what we will call Stokes formula for force in the sphere. So the rest are viscous components. Okay. This part is called, so this is buoyant force. This is so-called form drag. And this component is friction drag. So overall, F is equal to, when I put both drags together, this is Stokes' formula. For drag on the sphere. That's the magnitude, it's magnitude. And the direction is in the direction of the flow. All of that. Okay. This is what we were after, I think, for the past 2 weeks. Okay. So we basically developed. But it will help us, this entire, or knowing how to solve helps a lot in a lot of petrophysical. This is an engineering application, but in a lot of petrophysical applications as well. And I will go over where is it all used, this formula, next time. Since I went overboard last week, I'm going to finish a little earlier today, 5 minutes. Okay.